Since we have a exam tomorrow on quantum mechanics, let's go ahead and just review some of the basic stuff. Start over here with Hilbert spaces. And as we can see, we can sort of build them like this with different states. So we can think of like rolling a dice or flipping coins and stuff. So we can just do one state like this, or two states if you're flipping a coin, or three states if you have a three-sided die or something like that. And this, of course, could be more, but these are sort of the more basic ones because we generally tend to model the standard model, which is just particles or spins or energy. Well, energy could go up to many more states, so just keep that in mind. So then we have these wave functions, right? And there's, of course, the right side and the left side, but they're supposedly this vector that sort of lies around here, maybe pointing in some random direction. I'll just draw it here. And there's the wave function. We can see it's basically a combination of these two. Okay, and so the idea is that it's orthogonal, so the left side and the right side can sort of combine together. Um, and we have these operations that we do here. So a star a plus b star b equals 0. And to normalize it like this, we just say that if it's the same left and right, then it's equal to 1. If this is different than each other, so basically it's kind of hard to even understand this, but I guess the idea is that um, if if the wave function is in its own representation, then it can flip around. So you can have the bra and the cat, right? And that can normalize to 1. But if they're in the wrong representations, so um, how can we say this? Different eigenstates, I suppose. They're trying to combine together, then that's going to be 0. So it's kind of difficult to explain this, but yeah, if you have the same symbol on the right and the left side versus different symbols on the right and the left side here, then basically get zeros or ones. But this is only for the wave function, I believe here. We get different eigenstates as well. But yeah, so quantum mechanics is really confusing, but this is one of the first things that we need to know, as well as how to build the Hilbert spaces. These two things are important. Um, and then we can go on to maybe there's like different things like, okay, how do we like square e to the I theta? Well, that just equals 1. How do we take the star of 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 the conjugate of e to the I theta is e to negative I theta? Um, and this is what the right side and the left side of the wave function are. Again, this is just one wave function, but it has two sides. You can either take the right side or the left side to get the same, normalized wave function. So they square together, and that's essentially why we have to sort of always normalize this stuff and get the coefficient in front. It's kind of a complicated way of just trying to write out these different equations. Um, the math is a little bit easier. If we went through some examples, it would make sense, but we're just looking at some notes here. The idea is that we always want to normalize the wave functions. There might be some constant right in front of them, and we generally have to square both sides, set it equal to 1, and divide it by the square root. Okay, so then we have some other things here that are just basically little solutions of things like a like common results. A star minus a star a equals 1. And that can also be represented in this notation here. These are different things in the future. Like this is annihilator and creation operator. So these are sort of things we'll come back to maybe later. But for now, we can sort of ignore them. And these are some commutators over here. And some spins. So this is a little bit more advanced things that maybe wouldn't make too much sense, but we can talk about commutators. The idea is the commutators is we can write this notation here that maybe alpha that's a constant and a that would be a matrix alpha a comma beta b, and that's equal to this. So you kind of pull out the constants and then you have to do AB minus BA. So that's the operator here that we do this commutator situation. And here's some other ways that we can do commutators like A squared B, A, B, C, whatever. There's different ways to write these. And it's just kind of matrix algebra. So just some things to take a note of. It's not necessarily something we really have to remember, except maybe this one. You can simplify this by taking out the alpha and the beta. So then we have, we're kind of getting into the next level of stuff. The next level of stuff has something to do with spins. So maybe we'll take a look at observable operators at this point. The observable operators, basically, what can you measure on this wave function? Like, what kind of information can you pull out of it? Um, and basically, the operation is you're going to have a new wave function that's adjusted after you yank out the information from that wave function right here. And the operator A, you can write it like this. It's going to measure real eigenvalues, so we have to find some real values that we're going to pull out of this imaginary wave function. You can see that it's built off of imaginary components. Um, and so you can write it like this. I know it's kind of some weird looking math, but yeah, I know it's kind of the point. But let's look at this one. So this is basically a level one state wave function. So we take this matrix, and there's only one value in the matrix, so it's just A11. And this x here equals A times psi, which equals A times psi. Well, this is the notation that we kind of need to use. And over here, we have that if we take the operator and we act on this wave function, or this eigenstate right here, there's only one eigenstate, 1, then it equals the value of that matrix right in there times the eigenstate. So we're just basically pulling out information. We're just acting on that wave function. We're pulling out the information that's in there. Okay? So we can do that in level 2 here, sort of this two-state system. And same thing, so we take the matrix multiplied by the wave function. And well, the matrix has 4 values, although usually these two could be usually 0, so you only have 1 and 2. But there's different, here's some basic ones over here. Usually it's like 1, 1. Okay, so this would be like maybe energy level 1, maybe energy level 2, something like that. And then those are the values that we have in here. And all we have to do is we have to act on the wave function. And it's acting here on 2 different states. So it's acting on this state, or it's acting on this state. And of course, the wave function itself could be in either one of those 2 states. So if you act on the wave function in this state, then this is the result. You take A11 plus A22 and multiply those by those. If you have this acting on the wave function, then you pull out these results. Just a notation and the way that we have to write this, depending on whether it's 1 or 2 or potentially even 3 states. When we get into the 3-state system over here, we can see a huge matrix. We have to pull out 3 different pieces of information. That would be how the operator acts on the 3 states, 1, 2, and 3. And that gives us this 1, A11 for this 1, A12 for the 2, and A13 for the 3. Well, uh, this is kind of a nice little grid to look at because it kind of shows you how you'd want to write out all these components. Okay, so that's all. Now, yeah, we kind of have to sort of consider what the Hermitian stuff is. Is it's just a conjugate transpose. So let's say you have a real value and a conjugate value in your wave function. And sort of real value Well, the conjugate of this, as you can see, would be something like here's a plus IV and a minus IV. Although do remember that if we're doing it with a conjugate, just means taking the star. If you do that with a with e to the I theta, then it's e to the I negative theta. So that's kind of interesting. Um, so this wave function on the right is going to be a row matrix. So here's like two different rows. You have row 1 and row 2. And the bra, which is on the left side, is going to be equal to the um, column matrix. So we have two columns here. But you write it out like this vertically here and horizontally here. If you're taking the what is this called again? The dagger. I guess we should mention that this is dagger. I guess I don't know. Whatever. This is the Hermitian dagger right here. If we use this on the wave function, we're just asking what's the other side of it. So we're flipping it back and forth like this. And the other side of it shows us that we're taking conjugate parts of A and B. Notice we had to flip it. So we had to flip the vector sideways here, rotate it, and then we take the star and the star. And so we kind of write it in different notations, as you can see. There's another way to write it like this. And so you can do that with the right side, you can do that with the left side. And this is how you sort of take conjugate transposes and stuff. It's just the notation we have to keep very close track of. And here's another interesting operation you could do. A B dagger is equal to B dagger A dagger. Cool. Now, these values that we're measuring from these wave functions, let's just say for now that we're trying to measure like the normalized values. So we're just pulling out ones or zeros or i's. So we kind of want to consider these Pauli matrices that just have those values of 1, 0, and I, which just kind of normalizes things for us. Um, so here we can write the matrix 1, just regular old 1. If we want to write it as a 1 by 1 matrix, we don't really need a matrix for that. We just write the number 1. But if we get into two-dimensional matrix, then we have to write it like this. To three-dimensionals, then it would be written a little bit more in 3 dimensions. I don't think I have one here. But we can also rotate this matrix and look at it in the x direction. We look at it in the y direction. We look at it in the z direction here. And we can see that we have ones sideways here, ones on diagonal here, and the I with a negative I on this side. All right then. Again, this is just kind of a two level one. There's only 3 of them. These are the Pauli matrices in 2 dimensions. This is yeah. So we can take it into the 3rd level, and it becomes something like this: 1, 0, negative 1. Because we usually need the 0 value in there as well. We're taking it into a 3-dimensional matrix. As you can see, as we go into the 3rd dimensional for SZ, for example, we take our 1 by 1 and we multiply it by h bar. So we're taking h bar. If we're in 3 dimensions, we usually use h bar. If this is a spin 1 in 3 dimensions, and if you're doing spin 2 by 2, then it'd be a spin 1 half. So you get values of maybe h bar over 2, negative h bar over 2. This is the SZ matrix. Or you could get something like h bar, negative h bar. I think this is supposed to be a plus 1 right here. make more sense. All right, and so then this thing right here is another way we can write it in the y notation, or if we're doing it in the x notation, we kind of have to write it like this little triangle, this little star here. Okay, it's like a diamond, I guess. These are little diamonds. So these are the Pauli matrices, and so these are how we sort of extract values from from these wave functions, specifically spin values. These Pauli matrices extract spin values. I think in the third dimensional ones, there's a lot more than just three, but I'm not entirely sure about that. For now, we just kind of consider these. Here are other ways to represent them. Problem is that there's different ways to represent these things, and so we just have to consider that they may be written in these very strange notations, like alien languages. Okay, again, here's another way to write this. It's just alien languages, to be quite honest. And over here, this is the operator A. So instead of writing a 1, we could write the operator A. Remember, this is what measures our value, pulls these things out, and it kind of gives specific values to this, um, to these matrices, instead of just zeros and ones. Let's see. So this thing right here is basically trying to take a Pythagorean theorem in 3 dimensions using S. And that's the spin values, although of course it could work for anything, I guess. There's spin, there's angular momentum. Here are the 3 different types of particles that we might find. S equals 0, S equals 1, and S equals 1/2. So we don't usually don't even worry about this S equals 0 stuff. We'll just focus on these two, which is the 1/2 and the 1, which is either the 2 by 2 matrix or the 3 by 3 matrix. And um, this is a general way of writing SI squared. This is for individual spins. You can see that we just take S plus 1, and I guess we have H bar squared here. Because we're taking the square. Um, right. There's another thing over here, I guess. Energy eigenvalues. So like H equals E times the Pauli matrices. And so you can pull out M times BH bar. You have some constant over there, B. Here are some different ways we can pull out spin values and energy values. It could either be H over 2, negative H bar over 2, uh, H, negative H, 0, H times B, negative HB. And we even consider the states that we found. So we found the state 1, we found the state 0, we found the state negative 1. And that's what causes these values to be linked out. Um, if we take the energy and we take SI, usually this comes out to 0, keeping in mind that it has to be um, it has to be along the same no, some of these kind of forget a little bit. This one, I think they have to be along the same dimension if you're trying to commute the energy and the spin. So this should be in the I direction, this should be in the I direction, they should be in the same direction. There's probably enough for the second level stuff over here. Here's some more commutations like x and p or whatever. Let's perhaps go on to this momentum stuff. Consider all these different ideas that if we have momentum in position, if we're in the in the position space, then we kind of just take maybe x and we multiply that by x, uh, the x state, and we just pull out the x value from the x state. Um, if we're taking the opposite side here, then we have to be careful because it just means the dagger. But of course, if we do that, then it flips it around and pulls this value out, so it's fine. There's no uh, positive or negative here. Sounds like I'm talking nonsense, but anyway, let's go over here. So basically, if we take the momentum operator and we act on a position space, then we have to use this representation. So that gets subbed out. If we do the square, it kind of looks like this. Of course, it's the opposite if we're going to use the position operator on momentum space. We get all this stuff. And so we have to kind of consider Fourier transforms because we're transforming between position, momentum. So here are the different ways we can represent this. If we want to know the position space version of the wave function, we just have to represent it in position integral. We want the position, sorry, the momentum wave function, we have to represent it in the position integral. Use k, um, and then some important things to remember is this, like xp is equal to this normalized value here would be to the ipx over h bar, xp equals ih bar. Here's a way to represent this either the momentum states or the position states. So how do we find eigenvalues? Well, remember we kind of have to solve this equation here. And we can use eigenvectors and solve them here like this. This is kind of basic linear algebra stuff, just in case you need to remember. Um, Here's some ways to represent our results. If we find this eigenvalue and this eigenvalue, it means that we have to put it in uh, this state here. I'm not sure if this was supposed to be the E minus here, because that would make a little bit more sense. I think that would work right there. I'm not entirely sure. But over here, we can take expectation values. So if we take the expectation value of a Hermitian operator here, we basically just go 1, 0, 1, 0. Here's the matrix that we have to multiply it by. And if we did this specific operation, we would get just this one eigenvalue here, just because we have a 0 and a 0, 0. But that's just this one operation as a sample. Um, that's how you can calculate variance. Of course, you could do this with different things, not just h. You could put in any kind of variable here, like spin, um, or e for energy. But h is the same as e, so so that's interesting. Here's another way to again sort of do some of these operations. And here are some energy um, results. Usually we have to calculate expectations and probabilities, right? This is these expectations and probabilities right here. Take the probability, we're going to square it. And we could do it with a just regular numbers if we want to, but this is with a delta Dirac function. I think this is how we do it with regular values. So we could take like the square multiply. This is for expectation We're taking the probability right here and multiplying it by each value in the in the Hermitian matrix, the operator matrix. So those are the different possibilities that can happen, and then we're multiplying by the probabilities that we would get that result. Here's a little bit longer and expanded way to do that, but you can see here's a calculation where we're multiplying the probability times the eigenvalue, probability times the eigenvalue. And we always normalize these probabilities. The probabilities are always positive. And there's some energies that are important. Like classical energy, I guess, is 1 half times W squared, and then amplitude squared. The simple harmonic oscillator is just En is n plus 1/2 times h bar W. When we have a circle, we do n squared h bar squared over 2mr squared. This is the radius, this is the mass, and this is the energy level. Stern-Gerlach experiment. Well, we have to sum up probabilities sometimes, but that's like multiplying the probabilities. If you have multiple steps that you're going through, you kind of have to multiply the total probability. Is actually a multiplication there. I think there's a different symbol when we have to multiply. Not this symbol, but whatever. Um, Here is the way that we can kind of consider the Stern-Gerlach experiment. If we keep positive spins, that means that the only thing coming through the first level is positive spin in the z direction here. That means that this is the specific notation that we pull out because this is just how you write x plus z in the z direction. It just is. The thing is, sometimes these things you just have to know. There's no real way to just say it just is. This is the way that you write this. Uh, Gosh, and as we go into the second step here, let's say we wanted to pull out the plus in the n direction. Well, we have to use a little rotation matrix, which is cosine of this angle plus sine of this angle with the e to the I theta there, acting on the plus and the minus, and then we have to consider the probability by taking the left side of the n and pull it out of the right side of the plus z. And then we can square that equals this value here. And here's sort of the English way of considering this. We have to pull the now plus n's on the left side out of past plus z's. This is what there was, and this is what we want to know now. So we have to know what the past state was, and then we have to pull out the now things that we want to know. And this is kind of how we pull out probabilities. Then we can get into the next stage here, which is basically taking a look at maybe pulling out the negative z's. Again, this is sort of an example how you can write negative in the z direction, or you can write positive in the z direction. It's just the opposite. We have to be able to write like negative and plus minus ones and zeros in 2-3 dimensions. That's how we do it. And then now we calculate the probability here by pulling out the negative z's out of past plus n's. This stuff is crazy, but this is what it's all about. Okay, so I think that makes sense there. The idea is that after we measure one of these values, the wave function collapses to an eigenstate. So all of a sudden, we have let's see here we collapse the state to an eigenstate. So we measured the wave function. It was maybe this state here, and we pull out this value here, x1. So then we collapse to this eigenstate here. And how do we say this? Well, this is how we say it. We just say that, okay, now that we've measured one value, it just becomes that value. So if we measure the plus value, it becomes the plus value. And we have to write it in the plus eigenstate. So where are the different eigenstates that we can end up in? Well, that was what this whole thing was. So basically, if you end up in the plus x or the minus x eigenstate, then you have to just like represent it like this. It's square root of, or the 1 over square root of 2, 1, 1. Or 1 over square root of 2, 1, negative 1, which equals this. If you end up in the y states, then you have to use a 1 and an I, a 1 and a negative I. And then you kind of end up with this whole situation here. If you do it with the plus z and the minus z, it's pretty trivial. It's just 1, 0, 0, 1. We noticed that. Um, okay, so let's say it was maybe 3 dimensions. Alright, that sucks, because now you have to do it in the x, you have to do it in the y. I didn't even write the y's, there's so many. But I did do it in the x here. Sucks if they're going to ask about the y states, because I wouldn't be able to do that. But we're over here and we're looking at the plus state, the 0 state, and the minus state. And then we kind of have these coefficients in front, and to kind of remember this. I mean, clearly we could derive all this, but it's just like, it's really hard. We just have to sort of have this sort of written out, and we have to refer back to it so that if we do calculations and things fall into this particular state, we can just remember what that state is, and then we can arrange that. This is just sort of the basic state, the normalized way. So we could apply it to spin, we could apply it to energy. And here's one that we can apply to energy. Energy plus, energy minus. And expectation values for the energy. Here's another way to calculate expectation value. And here's another way to pull out probabilities. It's just kind of like the official way to write it, I guess. Generalized. Okay, so now we've collapsed the particular states, and it kind of sucked because when you do that, you have to rewrite it in these crazy ways. But yeah, instead of the z way. The z way is the easy way, and these x, y directions are all messed up. Here's another official way to write probability. So let's move on to this unitary stuff. What happens is things move over time, because usually it's just kind of stuck in one state. But we need to evolve this over time. So that involves taking a U matrix. And this U matrix is always equal to 1. But U star U is equal to 1. Use U, sorry, U dagger U is equal to 1. U dagger is equal to the inverse of U. And here's some different ways to write all these values. Unfortunately, I think my computer's freezing up right now. Just give me 1 second. Just close this. Open it up one more time. Pretty much almost done here. Just need to look at step 4. Uh, this isn't actually physics 130A. Like it's 4A. Actually it's 4A. It's physics 4E level. Um, how's it going? And thanks for showing up, sir. So that was pretty cool. But let's go ahead and continue where we are here and heading into the unitary stuff. So again, stuff over time we have to take our wave function and take a time derivative multiplied by I h bar. Gives us their energy. That's interesting. Or we could evolve it like this. We could say that the time value, the wave function is equal to u times the t equals 0 wave function. This is the original wave function. And then we could evolve it like this. So e to the I, no, negative I, this is energy here, t divided by h bar. So this is some important ways to write this. Now this is probably the best way right here. And then take a look at new negative t's. We're going to do that. Some different identities essentially. U conserves probability, so the probabilities always remain the same over time. Um, and I think we write them out like this. So we have to take like energy plus, energy minus, and then sort of represent them in their two different states, where we have a coefficient, e to the I with the energy, and then it's the first state, another coefficient, e to the I, and then that state. So there's always sort of split them apart into different states with their own coefficient and their own energy level. And this is just for maybe two energies, but there could be more. These are just some more complicated ways to write this, just in case. For example, plus minus n, then what are we doing here? We're pulling plus minus n's out of plus minus z's, and we get things like this cosine of theta, sine of theta, and that's just because we have to use this matrix right here, the change of basis matrix. We have to do all these different rotations sometimes, and we have to sort of remember these uh, identities, I guess. Or I could do the calculations, but it just becomes a little bit hectic. So then we have u. What is u? U equals negative e to the negative I theta. And then we have to put the Pauli matrix over 2. So that equals this. If we're doing a 90-degree rotation, that's important to remember because we use pi over 2 here. I'm not exactly sure how we did all this, but this is just an example. Alright, so if we go from here, I think we've pretty much, some other random stuff. Here's another example of going time, evolving over time. Here's like a time evolution of the plus and the minus state, divided up there as we saw before. I don't even know where this even comes from. Some of this stuff just gets a little bit confusing. So I don't know. It's just kind of just like examples of some math in this language. This is like a totally different language, like I was saying. Okay, let's consider the composite system. Okay, we just figured out sort of the key things so far. I think the composite systems are probably one of the last few things. So again, we sort of covered state spaces and this stuff here, um, spin and commutators, observables, momentum and position, Hermitian stuff, um, probabilities and expectation values, some different types of energies, eigenstates that they fall into, how you represent them in the different bases, how to take the time evolution of the wave function, and finally we're going to get to the composite system with the, well, there's two things, but this is the second to last thing. We're going to get to the composite system right here, which is like tensor products. This is how the sum of the tensors work, like this. Little X with a circle is kind of cool. Anyway, so we have the wave function maybe like this. Here's an example. how we can combine. This is gonna be like crazy stuff. Because remember that we have like the singlets and the triplets that pop out, right? If we're doing composite states. So basically, how do we get a state of 1? We can sum up two halves. So 1/2 plus a half equals 0 plus 1. So that gives us the 0 state, which is just a singlet. Here's the 0, 0. I guess you could think of this as the Higgs state, maybe. But whatever, so this is the singlet state, and then you can see what it looks like. Plus, minus, 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 plus with a 1 over square root of 2. I think the energy of the 0 state is 0. This just gets really confusing at this point. And then we have the singlet state, which is just S1 M. And the M could change depending on whether you're at 1, 0, or negative 1. So you start with the 1. This is the state, the triplet state. And then you have the three different types, the 1, 0, negative 1. It can be written like this, plus, plus, minus, minus, 1 over square root of 2 with all this stuff. And we have like energy of a 1 here, for example. Energy 0 here. I think all of these they all have the same energy, the 2 h bar squared, or that would probably be the spin, that's not the energy, but like, they would all have the same energy, and this has root energy. I guess this is the spin, not the energy, so the spin of 0 has 0, of course, that makes sense. The spin of these things are 2 times h bar? Not entirely sure. Stuff gets a little bit confusing, like I said. Uh, Here's an interesting equation. So spin equals SA minus SB. If you're trying to combine the two spins, plus SA minus SB plus 1 in combination with SA plus SB. Oh my god. Uh, what else do we have? Um, well, this is just a combination of states, so it's a little bit weird over there. But let's go on to the final thing, which is probably the most important, because now we can get into the really, like, what's the point of all this? Well, let's say we have a box, and usually it would look something like this. That's kind of a crappy box. This box might be a little bit more likely, but maybe put a little bottom to it here. So that's a nice little box. Bottom. So this box right here has walls, as we can see. And considering we're looking at this particular wave function right here, this isn't necessarily exactly correct. This would be 0 right here. This is sort of the 0 level. So maybe it shouldn't have been best to draw that. Whatever. Get rid of all that. This is the 0 level of the box right here. I don't really want to draw that part, but hopefully we can imagine it. It's 0 here because these are the nodes. This is the part where the wave function is actually equal to 0. Um, but this is essentially like a wave function in a box right here. If we had this type, it would just be equal to a constant, so that kind of sucks. But here's where we kind of wonder, okay, what should we do? We should maybe normalize this, try to figure out what the constant is before it. This might be an important um, identity to know. The expectation value here is how we calculate that. Oh, we could do it with the expectation value of x is equal to this cool thing here. We take the wave function left and right side, and then we just convert it into this. Um, so we can expand the wave function into energy eigenfunctions. We use this notation to figure out what the wave function is equal to in these different energy eigenfunctions. And here is the energy eigenfunction. And so if we wanted to pull out maybe the x value from the first energy level here, we can denotate that as 2 over L sine of pi x over L, as we can see here. This is a really important representation. Um, so the quantum harmonic oscillator is interesting. We can use this annihilator and create the annihilation and creation operators, A and A dagger. Uh, well, let's just kind of finish this up real quick here. As you can see, different ways that we can operate on the n plus 1, and the n minus 1 with the A operator. It turns into these things. Or if we did it with the creation operator right here, it would turn into these things. To use A on the ground, it equals 0. If you take n times n plus 1, it equals 0. And this is really important as well. You take any state and you look for the A expectation is 0, as well as the A dagger expectation is 0. And here are some more examples of how you can sort of take these A's and these A squares and A daggers and act upon an N state. But I think this kind of covers most of the things we probably want to know for for the exam that's coming up soon. Now it's probably not going to be enough because this is still really really hard. Nice man. Thanks for coming through. Sai Sashank. So basically, here we are. This is we can kind of go through maybe an official overview, I guess. These are some important things to remember: the Hilbert space and Dirac notation, the operators, measurements, commutators, the spin, the tensor products, the time evolution, positional momentum, and the quantum harmonic oscillator. So all these things should be familiar at this point. And yeah, here's a grand look at all this stuff. We can see that this has to be separated 1, 2, 3, 4, and 5, because these are the 5 postulates of quantum mechanics, that wave functions exist in Hilbert spaces, that there are observable operators on the wave function that can act on the wave function and pull out um, measurements. And as soon as that measurement has been made, it collapses to an eigenstate. Once it's in that eigenstate, there are these different probabilities based off those coefficients and stuff. So we can measure things like, remember the probability and the expectation value of energy. And then, of course, over time, this stuff evolves, and we have to use the unitary operator, so e to the I, negative, negative I, h bar, or h, whatever, all this stuff right here that acts on wave function. And then we could make this a composite system if we take two different, like a 1/2 and then 1/2 and combine them together to make a one state. So that just becomes a little bit more of a confusing mess. And of course, we can simplify things a little bit and try to put it into a real world situation by considering a simple wave function in a box or a quantum harmonic oscillator and try to use some annihilation and creation operators to simplify things. Pretty cool stuff. All right, guys, thank you so much for watching, and shout out to Anne Ukral and Sai Shashank for showing up.